The diesel engine is a powerful, operationally reliable engine, which is able to withstand heavy punishment in grueling transport conditions and can cope with extremely demanding operating conditions. Engines and complete vehicles undergo constant development, and this process of development continues unabated. Modern vehicles are extremely reliable, easy to drive, and their engines have a long service life. A driving distance of up to 1 million kilometers is achievable before anything needs to be done to the engine. The content of this film is generic and can be applied to any diesel engine, but we have chosen this engine to show you how a diesel engine works. This is the Volvo Group's 11-litre engine. It is a 6-cylinder unit with a displacement of 11,000 cubic centimeters, or 11 litres. Let's have a look inside the engine and see what happens. A diesel engine is a combustion unit, and the principle is to obtain rapid combustion of diesel fuel in an enclosed chamber above the piston. This combustion increases the temperature significantly, thereby increasing the pressure which pushes the piston down, giving it a great deal of power. It is this power we need. This is what propels the truck, boat, or machine. However, the piston just moves up and down inside the cylinder. We have to convert this vertical movement into a rotating movement. To achieve a rotating movement, a connecting rod and a crankshaft are used. Our engines are 4-stroke diesels. To put it another way, you could also say that the process, what actually happens inside the cylinder, occurs in 4 strokes. Let's take a look at the way the engine works according to the 4-stroke principle. We must begin by defining a stroke. Well, that's simple. The distance the piston travels from one dead center to the other is the stroke. And the dead centers are the positions in which the piston turns upwards or downwards in the cylinder. This is 1 stroke, when the piston moves from top dead center to bottom dead center. And this is another, when it moves from bottom dead center to top dead center. It takes 4 piston movements or strokes like this to complete the working cycle in each cylinder. There is one more thing. To initiate combustion, any combustion, the following are required: fuel, oxygen, and heat. And this also applies to an engine. The first stroke, the induction stroke, involves the supply of air, or in fact, oxygen. The piston moves downwards and the intake valve in the cylinder head opens. The air is forced into the cylinder. This cylinder filling process continues the whole time the piston is on its way down towards bottom dead center. When the piston has turned at bottom dead center and is on its way up again, the engine moves into the second stroke, known as the compression stroke. The intake valve closes and the air is trapped inside the cylinder. The air is compressed by the piston and the temperature of the air increases as a result. As the engine approaches the end of this stroke, the temperature rises to between 700 and 900 Celsius, which is sufficient to ignite the diesel fuel. When the piston reaches top dead center during the compression stroke, atomized fuel is sprayed in through the injector and combustion begins after a couple of thousandths of a second. The temperature and the pressure above the piston are now increased dramatically. The piston is turned at top dead center and it is pushed down with tremendous force. This force is transferred to the crankshaft via the connecting rod. The third stroke is known as the working or expansion stroke, as this is when the work is done inside the cylinder. All that remains is for the burned gases, in other words, the exhaust gases, to be expelled from the cylinder. And this is what takes place during the fourth stroke, the exhaust stroke. The piston is on its way up again and forces the exhaust gases past the open exhaust valve and out into the exhaust system. When the piston reaches top dead center, the cycle starts again. In with clean air during the first stroke. Compress the air during the second stroke. Inject the fuel at the end of the stroke. Get the engine to work during the third stroke. And expel the exhaust gases during the fourth stroke. This description only shows what happens in one cylinder. So, what happens if the engine has 6 cylinders, like our engines do? Well, it goes without saying that the same cycle occurs in all the cylinders. The expansion strokes from the cylinders follow one another in a predetermined order, which we call the ignition sequence. The pistons in the first and sixth cylinders move up and down together. So do the pistons in the second and fifth cylinders. And the same thing applies to the pistons in the third and fourth cylinders. The design of the crankshaft determines these movements. We will slow down our engine to show you the ignition sequence. The first cylinder from the front is known as number 1, and we will start there. Ignition. This is followed by fifth, then third, sixth, second, and fourth. Watch a few turns of the crankshaft and you can see for yourself. The valves have to open and close at exactly the right time. This is necessary to give the engine its excellent performance and to make the exhaust gases as clean as possible. All the parts associated with the valves are known collectively as the valve mechanism. The camshaft is an important component. The cam lobes on the camshaft lift the rocker arms, and this movement is passed on via valve yokes to the valves, which open. The strong valve springs help to close the valves. On this engine, the camshaft also controls the 3 high-pressure pump injectors of the fuel system. The camshaft is driven by the crankshaft via gears, which are positioned here at the rear of the engine. The device containing the gears is known as the engine timing mechanism. This timing mechanism is enclosed in the timing gear cover. The camshaft is driven by the crankshaft via the 2 idler gears here. However, the camshaft is not the only thing that is driven by the timing gears. Some engines are equipped with an optional power takeoff or PTO unit, which is driven by this double idler gear for the camshaft. There is a third idler gear, which drives the compressor for the brake system, the pump for the power steering system, and the fuel feed pump. The oil pump for the engine lubrication system is driven directly by the crankshaft gear. In order to increase the efficiency of our engines, they are equipped with turbo compressors that increase engine efficiency by supercharging, pressurizing the inlet air. It is the energy from the exhaust gases that drives the turbo at one end. At the other end, this energy is used to force more air into the cylinders. Now let's have a look at the lubrication system. Needless to say, all moving parts in the engine need to be lubricated. The oil pump draws in oil from the oil sump and forces oil out into the engine lubrication system. First through the oil filter and oil cooler to a main oil line which is bored through the length of the cylinder block. Oil is then forced out from this main oil line through ducts to the main bearings and onto the piston bearings through ducts drilled in the crankshaft. Two of the timing gear bearings are pressure lubricated. All the gears and the timing mechanism are also splash lubricated. The valve system and camshaft are lubricated through a drilled duct in the rocker arm shaft. The oil performs a number of other tasks in addition to lubrication. One of them is to conduct heat away from the engine components. The pistons, for example, get very hot when the engine is working under heavy load, and they have to be cooled by oil. This engine has an oil line for piston cooling, which is bored through the length of the cylinder block from where the oil is sprayed up under the piston through nozzles. The oil absorbs the heat, which is then cooled in the oil cooler. Despite this, it is the cooling system that deals with most of the heat in the engine. There is room for coolant around the points where combustion takes place. This space is known as the water jacket, and it is found around the cylinders and up in the cylinder heads. The water jacket is connected to a radiator, and a coolant pump maintains circulation in the system. The fuel system is manufactured with extremely high precision to perform its tasks. It has to inject exactly the right amount of fuel at the right time. Yes, that's right, at the end of the compression stroke. And the fuel has to be sprayed in by the injectors under high pressure, so that it atomizes in the hot air. A modern diesel engine uses a common rail-type fuel system. Let's have a closer look at how a basic common rail system works. These are the components of the system: fuel tank, pre-filter, fuel pump, including feed pump and high-pressure pump, main fuel filter, common rail and injectors. The fuel is drawn in by the feed pump from the tank unit, up through the pre-filter and the water separator, where water is separated from the fuel, and then into the fuel pump. There is a feed pump inside the fuel pump which pressurizes the fuel to a low pressure and leads it to the main filter. Here the fuel is cleaned, and the clean fuel is then led back to the fuel pump inlet. The fuel pump builds up a high pressure which forces the fuel up to the common rail and to the injectors. Fuel injection is performed by injectors, one for each cylinder at high pressure. Injection timing and the amount of fuel injected are controlled by the engine control module according to the firing order 1, 4, 2, 6, 3, 5. All fuel systems also need a return line back to the tank, This line is used to lead fuel back to the tank in case of overpressure and leakage. If we look at our 11-litre engine, we can see that this common rail system has a slightly different setup. Instead of a high-pressure pump, 3 of the injectors have been equipped with pump units driven by the camshaft. In addition to injecting fuel into a cylinder, they also contain a separate pump element that supplies pressurized fuel to the common rail. The other 3 injectors only have one job: to inject fuel into the cylinders. The feed pump can be found down here. The pressure from the feed pump is not particularly high, around 5 bar or 500 kilopascals. The common rail pressure, however, is around 350 to 2400 bar. The engine must be given exactly the right amount of fuel, an amount that matches the speed of the engine and the engine load. There is one more thing. Each injection requires different amounts of fuel for optimized combustion. The common rail fuel system has the following advantages. Fuel pressure is not dependent on engine speed and load, which means flexible control of the injection amount, injection timing, and number of injections. High injection pressure and good fuel distribution are also possible at low engine speeds and loads. Capacity to deliver smaller and more frequent injections, which results in reduced exhaust emissions and noise level. The fuel system, including injection quantity and injection timing, is controlled electronically. The system is called EMS, which stands for Engine Management System. The central part of the system is the Engine Control Module, or ECM, which contains unique software for the specific engine and installation. The Engine Control Module requires continuous information from a number of sensors on the engine. For example, coolant temperature or flywheel speed. It also requires information from the vehicle or the machine, such as engine start and stop requests, or accelerator pedal position, in order to control the amount of fuel and the injection timing. The Engine Control Module also contains engine protection software, which protects the engine from damage. In the event of a critical condition, the engine is temporarily restricted to protect the driveline. It is important to understand that the exhaust of an internal combustion engine like the diesel engine contains toxic gases and particles. In all engines produced by the Volvo Group, these have been dramatically reduced by hardware as well as software optimizations. Tough emission legislation in many countries requires after-treatment equipment such as selective catalytic reduction, or SCR, and exhaust gas recirculation, or EGR. Our engines are high quality and are very highly regarded throughout the world. But competition is fierce, and we must continuously work hard to ensure that we stay ahead of our competitors.